Right. The power for all the instruments when running? What is the power for all the instruments when running?
The power for the instruments when all running, I don't have that number off.
Not just the instruments.
Everything.
Everything running. What is the power demand?
Oh, well, it depends on what is exactly running. It's not like everything is running.
What is the peak power demand you would ever see in the mission that you have designed?
A peak power demand, that's going to be shown in my presentation later on, but that is when we are conducting radio science, and that is approximately about 370 to 400 watts when we're using both the K and X band tweeters.
So if you weren't doing that, you'd be down.
It's approximately 297 watts.
You could run everything else straight off the RTGs.
Yes, that's when the spacecraft is sitting nominally.
If there are no further questions, I'd like to present the layout of our spacecraft. My name is Christina Gonzalez. Layout analysis was designed by Al Pellegrini and Barry Gonzalez. Slide, please. On the left side of your screen, you can see the structure of our orbiter spacecraft. There are 4 outer panels attached to the inner shear panels, transferring loads to the center thrust cylinder. One of the shear panels is cut off partway down, just to allow for attachment of our probe vehicle. On the right side of your screen, you can see our orbiter vehicle fitting inside the fairing, which had a maximum usable width of 4.6 meters. Slide, please. On the left side, you can see our probe attached to the vehicle, highlighted in yellow. Right, you'll see highlighted in blue the communications components. On top is the high-gain antenna used to communicate with the Earth throughout most of the mission. The helix antenna is located on the side panel, same panel on the probe actually. That's used for communications, or receiving communications from the probe once we've dropped it into Uranus. On the internal side of those panels are located the communications components such as tweeters and receivers. Those are located very near to those antennas. Slide, please.
Let's go back 2 slides.
Yes.
So, if your spacecraft is 4.2 meters outside, how do you fit in a fairing that's got 4.57 meter diameter?
It's 4.6 meter diameter, and so the longest width of the spacecraft being from.
It's diagonal, you got to worry about.
I would like to direct that question to the layout team. The diagonal dimension of the spacecraft does fit inside of the fairing?
Yes, it does.
How?
4.2 times 1.4 is over 5 meters.
I think that 4.2 is diagonal because the high gain antenna is larger than the box below it, and the high gain is only 3.5.
That's it. The high gain is only.
The high gain is only 3.5 meter diameter.
So you're telling me the dimensions are all done?
Yes.
Okay. I can deal with that.
Because if you look at the height, it's only 4.
You probably should get it fixed before you send the report to the customer. Okay.
In order to see our propulsion components, besides the thrust cylinder, we have a fuel tank and an oxidizer tank mounted to the sides of the thrust cylinder and the immersion tanks. Around the top and bottom of the spacecraft are 1 and 4 meter thrusters. Directly in the bottom is our 3500 Newton main thruster, and we also have 4 200 Newton thrusters located around the bottom and bottom of the spacecraft.
There's a slide there on that slide. They got 4 Newton thrusters and 200 Newton thrusters at the bottom, and the others are 4 Newton thrusters.
Okay, so I said 200 Newton thrusters, but this slide says 4. These are the 200 Newton thrusters.
Apologize for the confusion.
Thank you.
How many thruster failures can you tolerate?
For the 1 and 4 Newton thrusters on the orbiter, I believe we can tolerate at least any one failure and up to.
They can do 2 to 6 depending on which thrusters fail.
The 200 Newton thrusters, I believe we can tolerate 1 failure. The main thruster is crucial to our total mission survival. If we do lose it, though, we can perform most of the mission using the 200 Newton thrusters.
but you can do the probe,
Yes, we can
measuring
still,
without it.
we can still do the probe mission. And that will be brought into more detail later in the presentation. You can also see some of the piping for fuel lines on the inside of the spacecraft. There's also access port on the front for filling and draining at the launch site. On the right side of your screen, you'll see in purple the power components. Mounted externally are the ASRGs, there are 3 of them on the orbiter spacecraft. Internally, we have 3 ASRG controller units. The battery pack, which is kept near the ASRG to maintain its sensitive temperature requirements. We also have PCBU and a propulsion and communications. Slide, please.
Are those batteries, excuse me, sorry, those batteries, you say they're internal, right?
Yes.
How accessible are they, to be taken out? Workhorse batteries, 4 lines, as well as, and then we'll install.
I'd like to direct that question to David Foster, who did the integration request for this. The question is, how accessible are the batteries on the orbiter vehicle?
They're just inside the NAC panel, which is removable.
So they're just
So you look at that, thank you.
on the left side, you can see highlighted the two of the ADC components. We have 3 star trackers on the orbiter vehicle, 2 IMUs. The ADCS computer, we also have 5 reaction wheels on the underside of the top panel. And we have 4 sun sensors on the spacecraft. There's one pointed out, it's kind of small, you can't really, but they're located at the various locations on the spacecraft. Highlighted in green on the right are the CDH control boxes. Those hover cards that control the systems on our spacecraft, they're both identical. One is forward and side, please. On the left, highlighted in red, you can see our thermal components. We have several radiators, doublers, and RHUs, all designed to maintain the thermal requirements of our system. The shunt radiator is used to dissipate extra energy at the beginning of life produced from the instruments. In pink, you can see the instrument suite. Well, the majority of our instruments are installed onto one panel on the side of the spacecraft. On the back side of that panel, or on the other side of the spacecraft, is the undeployed magnetometer boom shown in this picture. Deployed, that magnetometer boom will reach 9 meters in length. You can see our model where the deployed slide, please. So for the UPS structure, we knew that the UPS needed to be spin stabilized, but we still wanted to make it easier for installing components to the sides, so we chose an octagonal shaped design so that we could have flat surfaces to mount components. To fit the probe underneath, we have a cone at the bottom of our thrust cylinder. So the thrust cylinder doesn't go all the way through to the bottom, it goes partway up and then the cone extends outward. So the outer panels still transfer the loads through the shear panels to the thrust cylinder, and the probe is attached on the underside of the cone. On the right side of your screen, you can see our 2 UPS vehicles side by side in the launch vehicle.
I have a question on that configuration there.
Yes.
You said you're going to launch each UPS delayed from each other, not simultaneously?
They will be launching in the same vehicle. They will be separating.
Staggered
Exactly.
separation.
Yes.
And you're going to do a spin stabilized UPS, you're saying?
Yes.
So as that thing's ejecting, is it spinning up?
I'd like to direct that question. No, it's not. I would like to direct that question to my teammates.
UPS is not spin stabilized until after we do all of our system checks, so they will be just separating the vehicle, essentially floating.
Okay, so that there's, because you got a lot of instruments that are protruding from the side, so there's no way that that thing's gonna like
Correct.
bump into the next one.
I believe structural analysis has gone into the analysis of the 2 vehicles next to each other in the vehicle.
No, the concern really is how do you have the set springs set? You know, what are the separation springs going to do as you start to drive out off the place where you connect?
mean, that was a concern for us. We're under the assumption, I suppose, that both vehicles are going to separate ideally from the launch vehicle without any sort of spin rate, and that is a requirement we will be putting on our payload attach fitting. But we do understand that there is a risk and a concern that those vehicles are near each other in the spacecraft, which is why we're trying to mitigate that by having some sort of a delay in the separation and not have them float at the same time.
But you essentially do the mission spin stabilized, is that right?
I'm sorry, what's the question?
The carrier, I used to call it UPS.
Yes.
That, you do the bulk of the mission is done with that spin stabilized.
Correct.
And yet you're separating with a 3-axis capability?
Yes.
That seems awfully overkill. I mean, why would, aren't you paying a big penalty to have a 3-axis capability on a vehicle that's essentially a spinner?
I would have to direct that question to ACS.
It has to go 3-axis stabilized after it drops the probe off anyways.
For the relay?
Yes.
And is it a real-time link to Earth?
No, it's sequential.
Is what?
It's sequential, but the problem is you have to change your spin direction multiple times from Earth to Uranus back to Earth, and you do have a penalty with that.
But because you can't store all the data?
No, we are storing the data. It's not being sent real time. It's all the data is sent up to the UPS and then sent back later on the next pass.
And you can't capture all the probe data while it's descending with a fixed attitude on the spinner?
The UPS is not spinning once it's at Uranus. It's 3-axis stabilized at Uranus.
But why?
Yeah.
Why?
Why? I assume because it was for easier pointing requirements, basically. We didn't want to have to deal with possible nutation error.
Oh, but I mean, this link is easy to support compared to all the others you're dealing with, so it seems, it doesn't, for me, right now, it doesn't pull any water. I mean, you can't imagine why you do it that way.
Okay, so you're saying it would be simple just to keep spinning, and we can still...
Typically, you do one or the other. It's either a spinner or 3-axis, you don't do both. And you make your mission work that way, because they're redundant systems.
Well,
It must be costing you all kinds of everything to do this that you don't need to do.
Okay, noted. I don't want to...
Hasn't your customer been developed about this yet?
These are all really good points, and we appreciate if you wrote them as action items so we can address them further, and it looks like we haven't completely addressed that issue.
We have.
Oh, the last thing real quickly on this is you have a launch vehicle adapter that can handle the two spacecraft side by side and the fact that the probes are in that same location. Did you look at the launch vehicle adapter at all?
We're defining requirements and specifications for our payload attach fitting and handing that to the launch vehicle provider. Correct me if I'm wrong.
I'll be discussing that a little bit more.
Okay.
You know, some of the traits, well, we can get to that option.
I actually have the opposite question. It seems like a complicated vehicle to get the spin axis correct the way you have it right now without providing ballast.
Yeah, so there's a few mass properties issues, and we're still actually working on the layout of the UPS. But as of now, it actually requires 28 kilograms to balance it for spin.
So I thought that this was going to be a Delta 4 heavy
Yes.
launch. So what's with the largest width of the fairing is 3 meters? That doesn't sound like a Delta 4 heavy.
Those dimensions are the largest width of the vehicle inside of the fairing. So it's just saying that from the star tracker to the end of the AXRG is around 3 meters. It's not necessarily anything to do with the fairing dimensions themselves.
Have you guys looked at stacking them?
Yeah.
Yes. That was addressed early in our design phase, and we decided that that was not feasible for our mission.
Okay.
You know, as long as that you guys look at having them on a structure such that they don't point in the thrust direction of the launch vehicle, but they're some other angle, so that you can avoid this problem of banging into each other when you deploy.
You mean like building some kind of adapter such that they would be...
Yeah, a little bit. Yeah, something like that maybe. So
no, that would be interesting.
There's a high gain antenna similar to one on the orbiter. It's used for communication storage. There's also a helix antenna for listening to further transmissions. And the internal components are located near the antennas on the inside of the spacecraft. We also have two looking antennas located 180 degrees. Slide, please. For the UPS vehicle, we have one ASRG mounted on the side. We have a battery pack located here for thermal reasons. We also have an ASRG control unit located near the ASRG. For the UPS vehicle, we put the PCBU on the opposite side of the spacecraft because it is one of our more massive components. And so, for mass properties, we wanted to help balance that out as much as we could. In orange, we have the propulsion components. Inside the thrust cylinder, there is a tank, it's a bladder tank. It contains all the fuel. Mounted to the side of the thrust cylinder is a helium pressure tank. Along the top, we have 1 Newton thrusters, and on the bottom, so there are 2 4 Newton thrusters on opposite sides of the spacecraft. The box in the front has 2 1 Newton thrusters pointed off at angles, and 1 4 Newton thruster pointing down. This box is the same on the front and the back. You can also see the fuel lines as in the orbiter, and there is an access fill drain valves on the front. Slide, please.
Any survivability announcements done on the ASRG with regard to micrometeor damage possibly?
I'd like to direct that question to the survivability team. The question was there any analysis done on MMOD impact for the ASRG?
So it was from my understanding with talking with the thermal team that the ASRG came with its own case, and this case seemed as adequate protection for the MMOD. I don't have the thicknesses available for each case currently with me. However, if you would like follow-up, I can easily address that.
So on the left side of your screen, you can see the ADCS components. They're in the field. We have 2 star trackers, 2 IMUs, and several sensors located on the spacecraft. In the center, there are CCH boxes similar to the launch and orbiter. They're slightly different to accommodate the specific needs of the UPS vehicle. And we also have thermal components, again, the radiators and heat pipes, a shunt radiator to dissipate extra heat as well.
So I have a question. So
Yes.
for your attitude determination and control using start factor when you're spinning,
Right.
for attitude determination, okay, question related to the spacecraft. Sometimes it's spinning and sometimes it's 3-axis stabilized. What do you use for attitude determination when you're spinning and stabilized?
I'd like to direct that question to the ADCS team. The question was, which parts are using while we're spinning versus while we're stabilized?
So we had to choose special start trackers that could compensate for the 5 RPM spin rate and still be able to determine attitude.
Did you find some?
Buy some. So you're planning to
According to the
start
spec
tracker?
sheet, they should be able to.
Can you use a couple of scanners?
Yeah, right.